So we are going to talk about this new form of induction technique called strong induction. So as we have mentioned during the tutorial, for strong induction, we usually need to prove two cases. The one is still the same, the basis case. So we want to show some basis case is true. For instance, we may want to show that P1 is true. And then we have a slightly different inductive case. So for this inductive case, we are going to show that, we are going to show what? We are going to show that P1 and P2 and ... and Pk would imply Pk plus 1. Then the resulting of, so if these two cases are proven to be true, then we can conclude in our valid argument form that for every k starting from this basis case greater than or equal to 1, then we will have this Pk to be true. Okay? So we will have two examples of this. Okay? So the first one, so we are going to use the example in the tutorials in this lecture note slides. So let me define what is Fibonacci number. Fibonacci number. Okay, by the way, so Fibonacci is what? What is Fibonacci? It looks like a name, right? So it is a mathematician. It is an Italian mathematician, but his last name is not Fibonacci. So this is Italian word, okay? So it means fib of Nachi. So it's the son of Nachi, something like this, okay? So his name is actually not called Fibonacci. So maybe his last name is called Nachi, and then the son of Nachi, okay, something like this. But this Italian mathematician has studied this problem. So you're assuming that the rabbit problem, I guess some of you have heard of it. So suppose that you have a pair of rabbits, so one male, one female. Okay, so they are very reproductive. So they will give birth so they get married. This pair of rabbits, they get married. Okay, somehow. So after 1 month, okay, they will give rise to a new pair of rabbits. So luckily, it will always be a male and a female. Okay. So their son and daughter somehow. So rabbit doesn't have any concept of like human. So the son and the daughter get married somehow, and then after 1 month, they will also give rise of another pair of rabbits. Is that okay? So you start with one pair. Okay, next month you get a new pair. Okay, and then this pair, because they have just given birth, so they will take a break. Okay, so they will take a break somehow like this. Okay, so we take a break, and then this one is newborn, but somehow after 1 month they will give rise to one pair of rabbits. Okay, so this is rabbit A, pair A. This is pair B. This is pair C. Okay, so A will take a rest so that in the second month and they will not give rise to a new pair of rabbits. But in the next month, so one more month, so C will give rise to a new pair of rabbits. Let's call it D. And A will give rise to a new pair of rabbits. Let's call it E. Is that okay? So it's like every new pair of rabbits, you will get a new pair of rabbits in the next month. But if you have given birth of a rabbit in this month, then you will take a rest and then have a rabbit here. So B will take a rest. B will not give, so B gives C, B will not give at this month, but B will get a rabbit at this month. D, E, so you have F, G, H, okay? Is that okay? Do you understand the point? Okay, so each pair of rabbit will immediately give a new pair of rabbits in the next month unless it has given birth in the last month. So they will take a break for just 1 month. So this question asks, okay, how many rabbits will you get after a year? Something like this in total. So assume that they never die, okay? Okay, so So at the beginning, you have just one, just A, okay? And then after 1 month, A will give rise to B. So a total, you will get 2. Is that okay? And then what? And then after 1 month, B will give C, and then there is nothing more. So after 1 more month, you have A, B, C. Is that okay? So it is 1, 2, 3. And then after 1 more month, A will give E, C will give D, B will give nothing. So we will now have 5. Is that okay? And then after 1 more month, then you will get 8. Is that okay? So what is the next number? And why? The next number, I will tell you, it is going to be 13. But why? How do you get this 13? Yeah, is there a way to reason? Yeah, how? Why? Yeah, this looks a little bit difficult to look at it. Okay. Is there a way to, so the next one is going to be 21, and then the next one is going to be 34. And in fact, every new number here is going to be the sum of the previous 2 numbers. Is there a way that we can reason why this is true? So A, let me see. Okay, so to reason this, okay, so how do you reason this? So let's take a look of how this 5 is obtained. Okay, this 5 is obtained by, so why it is equal to 3 plus 2. So this 3 represents what? This 3 represents the number of rabbits that is existing already in the last month, right? Right? And then how many rabbits you will get for this new month? It must be all the rabbits that are there in the last month. Because for all the rabbits that are existing in 2 months ago, each of these rabbits will give rise to a new pair of rabbits. Does that make sense? Is that okay? Okay, because you don't look at all the rabbits in the last month, because some of them are just newborn. So how many of them are not newborn? So it must be all the rabbits that are already there in the last month rather than the last month. So how do you get 3 and how do you get 2? Because there are 3 rabbits in the last month, and there are 2 pairs of rabbits in the last month. So any of these rabbits here will give rise to a new pair of rabbits. So B will, does that make sense? Well, it doesn't make sense, right? Does it? So how do you get this D? D is C, and this is A. Yeah, whatever. Okay, trust me. Okay, so my reasoning is wrong. Okay, but trust me. Okay, so this is how Fibonacci get his number. So perhaps I should give you a better example, but let's don't waste time here at this moment. But Fibonacci finally observes that, okay, to solve this rabbit problem, we are interested in this sequence. So the first number is 1. You may think of it as the next number is 1, and then the next number is 2. And for each number onwards, it is the sum of the previous 2 numbers. So 1, 2 gives me 3. 2, 3 gives me 5. 3, 5 gives me 8. 5, 8 gives me 13. And then 21, and then 34, and so on and so forth. Is that okay? Okay. So first of all, this number is growing. It's always increasing, of course. But are they increasing linearly or quadratically or what? So if we say some number is increasing quadratically, so it may be like the cave term. Let's say this is the cave term. It's close to some number times k squared plus some number. So it is, if it is of a form like this, some number times k squared plus some number like this, then we are saying that this sequence of numbers is increasing or is growing quadratically because it is k squared. Or on the other hand, if this looks like some number times k plus blah blah blah, then we call the growing is like a linear growth, so it is growing linearly. Or alternatively, if it is like something to the power k, something to the power k, 1 to the power, no 1, 2 to the power k, 3 to the power k, 1.5 to the power k, then we call this exponential growth. Exponential. So what do you think? Does it look like, so one of them is correct. Does it look like quadratic growth? Or does it look like linear growth? Or does it look like exponential growth? What do you think? So the next one is what, 55, right? What do you think? Is it growing? It's growing faster and faster and faster, right? It's growing faster and faster and faster, right? So it doesn't look like it is linear. So we can actually avoid linear. So linear always have similar growth each step. Okay, it's linear growth. Okay, 2, 4, 6, 8, 10, it is linear. 3, 6, 9, 12, 15, it is linear. Okay, so it doesn't look like linear. The gap is larger and larger, right? But it could be quadratic, it could be cubic actually. It looks like k to the power 3. Or do you think it is exponential? What do you think? If you think it is quadratic, could you please raise your hand? Okay, good. If you think this is exponential, could you please raise your hand? Okay, some. If you don't know, or you don't want to say anything, could you please raise your hand? Okay, good. Okay, thanks. Okay, let me tell you. Look at this. Okay. So everyone agrees that it is always, each term must be larger than the previous one, right? How can we prove it? We prove it by induction, okay, because everyone is a positive number. And then it is the sum of the previous two terms. So it must be larger than the previous term. So it is growing, okay? Now, each term is larger than the previous term. So if we skip the term, let's look at 1, let's look at 2, let's look at 5, we skip 13, 34, and then this one is 89, something like this. We skip the term. Then what do we have? This one is the sum of these two. This one is larger than this one, or equal to this one. So this term is greater than or equal to, so 2 is greater than or equal to 2 times 1. Does that make sense? Okay, this 5 is equal to 3 plus 2, but this 3 is greater than or equal to 2. So this 5 is greater than or equal to 2 times this 2. Is that okay? Similarly, this 13 is equal to 8 plus 5. Is that okay? 8 plus 5. And then 8 is greater than or equal to 5. So 13 is greater than or equal to 2 times 5. Is that okay? Does that make sense? So this 34 is greater than or equal to 2 times 13. Okay? So what do you think? So here we will see that if we skip the term, it gets double. So it must be growing exponentially. Is that okay? Growing exponentially. So actually the growth is greater than or equal to, so you double it each time and you skip a number. So it is like on average you are square rooting 2, increased by a factor of square root 2 for each k. So it is greater than square root 2 to the power k as k becomes larger and larger and larger. So this is the growth, and then this is one of the number that you can prove that it is at least square root 2 to the power k when k is large enough. If you are okay with this, could you please raise your hand? Okay. Okay, now the next one is, but then it doesn't look like square root 2, the actual number. Because 30 divided by 8, it is already 1, okay, larger and larger. So 34 divided by 21. Okay, 34 divided by 21 is like what? It's like 1.6, around this range. It is like 3 over 2, right? 34 over 21 is like 33 over 22. So it is like 3 over 2. Okay, 3 over 2. So it is like 1.5. But this one is 1.4 only. Okay, so this is not really the exact growth rate. So if you look at the numbers longer and longer, and then you get the ratio between any two terms, in fact, there will be a limit exists between the ratio of the two consecutive terms as this Fibonacci sequence, if we look at it for more and more terms. So what is that term? Okay, so here, let's look at the ratio. So the ratio of these two is 1. Okay? The ratio of these two is 2. Is that okay? The ratio of this is 1.5. The ratio of this is 1.66667. The ratio of this is 1.6. The ratio of this is what? 13 divided by 8 is 1 point what? 1 point, anyone? 1.6125, eh? 2 over 4, 625, something like this? Is it? No? Let me see. Is that wrong? No, it's wrong. 1.625, yes. Something like this. And these two, I don't know. I don't have a calculator. Okay, so you have something like this. Let me tell you, okay, in the limiting case, the ratio between two terms will be this number, this square root 5 plus 1 over 2. This number is close to 1.618. What is this number? Anyone know? Very good. This is the golden ratio. Okay, this is the golden ratio. So what's so special about this golden ratio? What is so special about this golden ratio? What? Pardon? It looks good. Very good. Why? Why it looks good? I would say a square looks good, right? So the ratio of 1 looks good, right? But golden ratio, golden ratio it looks good. Looks good. Why? Why? Why does it looks good? Why? It looks good. Okay. According to some people who draws. Okay. So what is so special about this golden ratio? So imagine you have a rectangle. So this is a rectangle. Let's say this is of this golden ratio 1, and then this is something like 1.618. Is that okay? If you cut a square from it, you cut a square. Cut a square from it. You get a new rectangle. This rectangle, this side is 1. This side is 0.618. And you will find that the ratio becomes the same. Okay. So this is why people, so if you further cut a square from it, so somehow you cut a square from it, then this part, you have a new rectangle, and this rectangle, the short side to the long side, will still have the ratio of 1 to golden ratio. Is that okay? So that's why that's why people will say this is something very nice. And then, so we have golden ratio, but we also have silver ratio. So what is silver ratio? Silver ratio, we use it every day. We have our A4 paper. So this is A4 paper, right? So what is so special about this A4 paper? So golden ratio is you cut a square and then you get the same shape afterwards. Silver ratio is you cut 2 squares and then you get the same shape. So you have a A4 paper. Okay, so what is the silver ratio? Silver ratio is square root 2, the magic number square root 2. So you cut a square, and somehow you cut another square, and then you get another, this one. This will have the same ratio as before. And then it turns out that the silver ratio is square root 2. Okay. Okay, so, okay. Yeah. So in general, so Fibonacci number is something like this. You have 2 initial conditions. Let's call the first number F0. So let me call it 1. You have the second number F1. Let me still call it 1. So 1 and 1. And we have Fk is equal to Fk minus 1, the previous term plus the term before the previous term. And this holds for every k greater than or equal to 2. Then this will define a sequence, the Fibonacci sequence. And why does it work? Why does it work? This is a ratio such that this ratio, this is the root of this equation, x squared is equal to x plus 1. This is a root. Okay? Is that okay? Okay, now, amazingly, we can have a formula that helps us to calculate what is the kth Fibonacci number. And then we are going to show that this formula is correct. So we are going to show that this is, we are going to claim, we claim that f of n is really equal to 1 over square root 5 times square root 5 plus 1 divided by 2 to the power n plus 1. So there is a typo in the slide, so it should be n plus 1 minus 1 over square root 5 times 1 minus square root 5 over 2 to the power n plus 1. We're going to show that this is true. And how do we show? Okay. Now to show that this is correct, what we need to show is, we need to show that it satisfies this formula. F0 is equal to 1, F1 is equal to 1. And then we also want to show that it satisfies the next formula. Fk is equal to Fk minus 1 plus Fk minus 2. Now, if this expression satisfies everything, then it must be the same as this sequence, because it defines F0 the same way, it defines F1 the same way, and it defines every other term the same way as this one. So these two are going to be the same. Is that okay? So what we need to do, we need to check whether F0 is correct, whether F1 is correct, and whether Fk is equal to Fk minus 1 plus Fk minus 2. Is that okay? So as long as these are proven, then this is okay. So here, you can think about F0 and F1 as the basis case, because these are the foundation case that we don't use this formula to define this F0 and F1. So they are the basis case. So let's take a look of F0. So what is F0? According to this formula. So F0 is equal to 1 over square root 5 times what? Times, let me copy square root 5 plus 1 over 2, because n is equal to 0, according to this one, minus 1 over square root 5 times 1 minus square root 5 over 2. Is that okay? So this is equal to 1 over square root 5 times square root 5 plus 1 minus 1 plus square root 5 divided by 2. So it is equal to square root 5 plus square root 5 divided by 2 times 1 over square root 5. So it is equal to 1. Is that okay? Is that okay? So F0 is okay. Now how about F1? F1. Let's see. F1 is equal to 1 over square root 5 and then bracket square root 5 plus 1 divided by 2 square minus 1 over square root 5 times 1 minus square root 5 over 2 square. Is that okay? Wow. Difficult. Okay, you can, yeah, if you trust me, then this is equal to 1. Okay. Okay. If you want to do the derivation yourself, okay, let's do something a little bit cleverer. A little bit, just slightly cleverer. Okay. So here, I'm claiming that this is the root of x squared is equal to x plus 1. So I'm claiming that this is the root of x squared minus x minus 1 is equal to 0. Let's check. So what are the roots of this quadratic equation? It is plus 1, right? Yeah, let me write plus 1 plus or minus square root of 1 minus 4ac. So it is 5 divided by 2. Okay? So square root 5 plus 1 over 2 is a root, and then there is another root. So this is one root, and there is another root. Let me use the yellow color. So another root is exactly the one that we are writing over there, 1 minus square root 5 over 2. So there are two roots. Okay, these two roots will have the same property that x squared is equal to, so they have the same property that x squared is equal to x plus 1. Okay? Good. Okay. X squared is equal to x plus 1, then we are going to use this fact. So this is equal to 1 over square root 5. This is x squared. X squared. So it is equal to x plus 1. X plus 1. X plus 1. Okay? Okay, and then minus 1 over square root 5. This is another root, x squared, right? And it has the property that it is equal to x plus 1. So it is 1 minus square root 5 over 2 plus 1. Is that okay? Is that okay? And then this is 1 over square root 5 times 1. This is minus 1 over square root 5 times 1. So this plus 1 and this plus 1 cancels. Very nice, right? And then what? This is what? This is the same as this one. If you look at it, the same. The same. Okay, if it is the same and this one is cancelled, then this must be equal to 1. Good. So we have spent some time, okay? And then we find that the basis case are all correct. F0 and F1, they are as expected as we want.